numbers. All right. Now, the proportion stuff had to do with categorical. You didn't recognize it maybe, but it does. When we do proportions, it's dealing with categorical data. When, like, how many orders were done on time, right? What percent of the orders were late, whatever. Averageable. So it says construct a 95% confidence interval to estimate the mean number of states a senior can name. Because if we only sampled 32, that's not all the seniors, right? We want to make an estimate of what is the truth. All right, so it's going to follow the same structure as before. The state, plan, do, conclude thing, which I might need to work on looking at your quizzes. But state the parameter we want to estimate. All right, the parameter we want to know is mu. It's the true mean number of states seniors can name. Was it in 1 minute, I think? Yeah. In 1 minute. And at what confidence level did we want to be? 95, thank you. 95% confident. All right. Now, plan. Y'all don't have to name the procedure. That's an AP thing. But just so you know, what we were doing before was the Z interval, right? One proportion Z interval. What we do now is a T, as in Tom, interval. T as in Tom. So the T interval works a lot like the Z interval. Okay, it looks a lot like the normal distribution, but we switched to the T distribution because it's averages, all right? And when we get to averages, we have a sample standard deviation that keeps us from being able to use the normal distribution. And there's a whole history behind how this thing came out. But what happened is the T distribution looks like this, all right? I'm going to do it. Oops. What is going on here? All right. This is the normal distribution, right? Not very, it's kind of crooked, but there it is. There's the normal. But what the T distribution does is it changes based on your sample size. All right? If your sample size is small, let's say our sample is like 10. The T distribution follows the same shape, but the ends are much fatter. Like there's way more room for error in the ends. Okay? If my distribution or my sample, let's say it went up to like 30, guess what? It's going to look a little more normal, probably this way, not better than the other one. It's getting closer and closer to the true normal distribution. The higher your sample, the closer it looks to the normal. Okay? There's a whole table you have to read on this, but y'all don't have to do that. It's in your calculators, right? But what you will notice when you use in your calculators, we won't use norm CDF, we'll use TCDF. And it asks you an additional question. Because the shape of this thing is determined by the number of in your sample, it asks you for DF, which stands for degrees of freedom. It's really easy to find. It's just your sample size minus 1. So when you enter it in, I'll show you, it's going to say, okay, what's degrees of freedom? Well, whatever your sample is minus 1. And that tells the calculator which shape we're looking at, and it will determine the area therein. Okay? That's the big difference between T distribution and Z. T is what we use for means. Z is what we use for proportions. All right? So you will hear that here on out. Oh, go away. Oh, this is going to be fun. Okay. All right, T interval. Check the conditions. Okay, also we call these assumptions, right? Some people forgot to do this on your quiz. Checking the assumptions. Do you remember what the assumptions were? Random sample, that's still in play. And what was the other one? We used the large counts test to prove it, but what were we trying to prove? normal, right? We're trying to figure out if it's normal. Large counts test is what we use with proportion. So now we're checking out normal, but we're using means. So large counts test doesn't work. So let's back up for a second. Was this sample taken random? We used it as a random sample. So we're going to say yes, okay? So we're going to say yes, and I always put the sample size here so I have quick reference. The sample was 32. Okay, normal distributions. How do we know if it's normal, if it's means? Y'all remember this? That 30 thing, right? If n is greater than or equal to 30, we know it's normal. Do you remember what that was called? Good, central limit theorem, yes. So in this scenario, we would say, since n is 32, which is greater than or equal to 30, by the central limit theorem, we know that this is approximately normal. So it's the same stuff we did in chapter 7. We're just applying it to this situation. Now we know we can use the t interval. All good. All right, on the do step, if the conditions are met, perform the calculations. They're always going to be met, so don't stress over that. The general formula, you don't need to worry about that, but the specific formula for means looks like this. You start with the x bar. X bar is now our point estimate. It's our sample. Plus or minus t star. It's no longer z star, it's t star. And the standard error looks like this. It's our standard deviation of our sample divided by the square root of our sample size. All right, and then we're just going to plug in our numbers. Okay, so we go back to the data set. What was the mean? 16.813 plus or minus. I'm going to leave a space for t star real quick. S is my standard deviation, so 5.527 divided by the square root of my sample size, which was 32. Now, to find t star, it's exactly the same thing as z star. Okay, if you remember, kind of envision this. You put your confidence level in the middle. So 0.95 is in the middle. What's in the tails? Yep. 5% split in half becomes 0.025. Yep. So let me show you. In your calculators, you're going to use inverse t. Inverse t, and it's going to ask you, okay, what's the area and then what's the degrees of freedom? So 0.025 is what we wanted. How many degrees of freedom would this set have? 32 minus 1 gives me 31. Easy enough. All right, so let's switch to my calculator. Same menu. Inverse t is number 4. 0.025, comma, 31. There it is. It gives me the negative, right, because it's on the left side. But remember, we want the positive and the negative. Oops. 2.04 is fine. All right, then I would start hammering out these values. So I'm going to start with the standard deviation thing. 5.527 divided by the square root of 32 times 2.04. Okay. So then I'm going to take 16.813 and I'm going to subtract that value. So I get 14.820. Copy, paste, take it back down, and I'm going to add it this time. And 18.806. All right, so there's that. There's my calculation part. Interpret your interval in the context of the question. Okay, this is that sentence that we need to know. So we would say we are 95% confident that the interval from 14.820 to 18.806 captures the true what? What are we trying to estimate here? Yep. Mean number of states. Oops. Students can name in 1 minute. 1 minute. Okay. So, does this ring a bell a little bit? Yeah? Okay. Let's look at the back. Let's just summarize this. So, when you do an interval for a mean, you state the parameter and the confidence level. So, it's always going to be the true mean something, whatever the question says. True mean number of states, true mean height, true mean weight, whatever. The plan step, it's a one sample t interval for mu. You don't necessarily have to remember that, but you do have to know these two. Conditions, and TW calls them assumptions, but it's the same idea. You have to check for random sample, and then you have to check for normal. So this is a throwback, chapter 7. You may not remember this. With means, there's 3 ways you can know it's normal. CLT is our favorite because it's the least amount of work, right? However, if the population is normal, that is one way you can know. And then here's your CLT thing. And then here's if the off chance of these two not working, you have to look at the sample distribution, like a box plot. Or there's a thing called a QQ plot that I'll talk about in the video. And you can just glance at them and know, is there strong skewness or outliers? If there's not, then it's normal enough. That's all it is. Okay, and those displays will be given to you on on a test or something, because I don't want you taking time to draw them out for that. But you have to look at it and you have to make a statement like, the sample distribution shows no skewness or no outliers. You're good. You're good. All right, and here's your formula that we just talked about. All right, so let's try this. See if we can do one. City council member wants to estimate how many pounds of trash households in their community produce per week. To determine an estimate for the standard deviation of the weight of trash produced, a small random sample of households was selected, and their trash was weighed on a garbage day. This produced an estimated standard deviation of 36 pounds. All right. Now, on part A, we're going to skip that because this is really section 8.4. We're going to come back to that tomorrow. Okay. So it's asking us how many households do we need to sample. We haven't done sample size yet. That's in tonight's video. So after solving part A, the city council realizes that it'd be too much work to weigh the garbage of that many households. They give up their hopes on estimating the true mean weight produced within 3 pounds, and they select a random sample of 15 households, and they weigh the trash for each of these households on a garbage day. Here's the results. So this is going to make us do all the work, all right? But it's not bad, I promise. Calculate and interpret a 95% confidence interval for the mean weight of trash of all households in this community. So we're going to walk through the state plan do conclude thing. I'll show you what you need to show for full credit when you do one of these. And then we'll be done, all right? So in the state step, what am I looking for? Mu. It's the true, I'm just copying the words from the sentence above, honestly. Mean weight of trash for all households in this community. And I want to do it with 95% confidence. That's all you got to tell me on state, all right? On the plan step, what I'm really looking for are the assumptions, okay? So let's see, was it normal, or I mean random? Was it a random sample? Yes. Yes, it was random, and n was equal to 15. Is it normal? Do we know? They didn't tell us population is normal, did they? Can we use central limit theorem? Sample of 15. So that's a big fat no, right? Wah, wah. So now we got to do the worst case scenario. Make a box plot, make a display, whatever. Easiest way to do it if you're doing it by hand is just make a dot plot. Trust, okay? I'm not going to ask you to do this on every question. In fact, most of them I give them to you. It's good for practice. Okay. So if I was doing a dot plot, a dot plot. I said it right. Okay, so let's look at the data. What's the lowest one? 26.5, maybe? So I'll make that 25. Oh, 19? Is it really a 19? Ooh, 19.8. Okay. And so that's the lowest, and the highest would be, is it 119? Okay. Sheesh. Okay, so let's just make that 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. And this would be pounds of trash. All right. It's only 15 dots. It's not like 50 or 100. We can do this. And you're just estimating here, okay? So that's pretty much there. 74, 80, 99, 31, 93, 18, 88, 46. Okay, so there it is. Pretty boring, right? Pretty flat, pretty boring. So what I do in this case, after I've done my dot plot, I would just make a little statement. I would say the sample data shows no strong skewness or outliers, so it's safe to proceed. Safe to proceed. And I have completely run out of space, didn't I? All right. On the do step. All right. I need some values, right? I need the average, and I need the standard deviation of this. So I'm going to need to enter this data in my calculator in a list. Do you remember how to get to your list? Stat edit. Okay, my lists are full, so I'm going to have to go up here and clear them out. I'm going to enter those 15 pieces of data in here. Okay, do you remember where to go from here? If I want the average of this data and the standard deviation, where would I go? Huh? Calc? How do I get to calc? Stat, over to calc, and then the very first thing, the one variable statistics, okay? And it should say list one, that's what I want. And here's my data. Now, X bar is what I want, so I'm going to write this down. X bar is 68.85, and then I need S. So my standard deviation is the S value, not the sigma, but the S. So 35.78. And I'm going to use those values to plug into my equation. So what do I have? 68.85 plus or minus something T star. Now, I'm doing 95% confidence, so while I'm in here, I'm going to do my inverse T. Okay, inverse T would be 4. All right, and I want 0.025. How many degrees of freedom would this set have? N is 15, so degrees of freedom is 14. It's just minus 1. So 14, boop. So 2.14 is my T star, okay? And it's going to generate for me, let's see what we get here, gives me 49.09. .61. All right, so there's my interval. All right, so then the only thing left I have to do is my conclude steps. I'm going to have to zoom in really fast and write really small. So we would conclude. Sorry if your space is messed up like mine. Can you see it?
Yeah.
Okay. Conclude. What does our sentence start with? We are 95% confident, right? We are 95% confident that the interval from 49.09 to 88.61 pounds captures the true what? What's wrong? Am I going too fast?
No, Dylan.
Just Dylan.
Yeah.
It's just Dylan. True mean, what are we estimating? True mean weight of trash for all households in this community. Okie dokie. Do you see how it's really similar what we just did with proportions, if you can remember that far back?